Now, why does this matter? Why is this such a contentious issue in our society today? Well, because if you take the biblical text straightforwardly, you will see that there's genealogies going back to Adam, and that takes place about 6,000 years ago, Adam's creation. Now, of course, Adam was created on day 6, and the Bible describes the universe, or at least the stars that fill the universe, being created on day 4, just 2 days before Adam was. So that would put the creation of the universe at about 6,000 years ago as well, at least from the perspective of an Earth-oriented observer. And indeed, all through the Bible, there's quotations from Genesis. Those who say it's not historical have a big problem here in exegeting the biblical text. For example, Christ himself quoted Genesis frequently, not the least of which was Mark chapter 10, where he said, "At the beginning of creation, God made them male and female," speaking of Adam and Eve. So God did not create Adam and Eve 13.7 billion years after the beginning of creation. He created them at the beginning of creation. So the New Testament affirms that creation happened thousands of years ago rather than billions. However, we're not told in our broader society, in our science education, that this is what actually occurred. For example, if you look up the age of the Earth in Google, you will learn it's 4.5 billion years old. And who am I to argue with Google, of course, right? Going further, the universe itself is supposedly 13.7 billion years. Interesting that on the day I took this screenshot, it so happened that some of the results were actually revisions of the age of the universe. But we'll set that aside. So in the creation evolution discussion, when it comes to the age issue, there's two primary contrasting perspectives. We have an Earth being presented to us as being 4.5 billion years old in a universe that's 13.7 billion years old. Contrasted with that is the biblical account, which says the Earth was created about 6,000 years ago in a universe that was also recently created, at least from the perspective of an Earth-focused observer. Now, to figure out which of these two contrasting perspectives is the better one, we need to talk about time a little bit. Now, this is an interesting question. It's a lot of things that we don't normally think about. Sir, you have a watch. Can I ask you what time it is? 8:30. Notice he told me a number. When I said, "What time is it?" he didn't say, "What do you mean by it?" What does 8:30 really represent? 8:30 represents the time it's been since noon, and ultimately, we're referring back to when the day started at midnight, right? So when we tell each other what time it is, what we're really referring to is the amount of time it's been since the day began. Now, we don't even think about this because clocks are ubiquitous in our society. I mean, there's lots of watches here. I mean, we have these things. In fact, I mean, clocks have gotten pretty amazing. I have a watch at home. The batteries ran out a couple months ago, and I took them out. Haven't gotten around to replacing them yet. But I found out that even without the batteries, this watch still tells the correct time. But only twice per day, yeah. Yeah, people saw that coming. So most of us in the room, if I asked you what time it was or how long has it been since the day began, you'd have a device of some kind or another that could answer that question. Does anybody have a device that can tell us how long it's been since the Earth was formed? Both creationists and evolutionists agree that the Earth did have a beginning. The question is, when was that beginning? Does anybody have a device that'll tell us that? What about the entire universe? Well, for that, we can't use these kinds of devices. And in fact, we can't even really use clocks or watches. Instead, we really need to use something like an hourglass. What do I mean by that? Well, sometime before this talk began, hopefully you can all see this, I have an hourglass here, and there's sand trickling down from the top to the bottom. How long has it been since I started this hourglass going? None of you saw it happen. None of you were there, right? So how would you figure it out? Well, all the measurements you can take are in the present. You can't look into the past to see when that was. And since I'm not telling you when that was, you can't use eyewitness testimony either. So you have to use good science and take measurements. What are you going to measure? Well, you're going to measure the rate of this process, the rate that the sand trickles from top to bottom. You're also going to measure how much sand is in the bottom, the amount that's there, and from there you can calculate how much time it's passed since the sand started to trickle. That makes sense, right? Now, how is this distinct from a clock? Well, the clock is more precise and probably more accurate than this would be. This is more rough estimates, of course. But my point is, this one has initial conditions that you weren't there to see. Because if you think about it, you have to assume certain things in order to use this as a clock. You have to assume that the rate of sand trickling has been constant since this thing was inverted, right? You also have to assume that you know the initial conditions. And you're probably doing this without even realizing. What do I mean by that? Well, if you walked into a room and someone asked you how long it had been, it's hard to even see this on this screen. This is the top bulb of an hourglass here. How long has it been since this hourglass began? Long time or a short time? Long time. Now, what if someone showed you behind the curtain there was actually a second hourglass, this one, and told you, again, you can't see the bulb here very well, and told you these two hourglasses were inverted at the same time? Well, how can this be? Well, it gets back to the assumptions you have to make. Constant rate. Well, you can measure the rates and see that they're both the same. What does that mean then? It means the initial conditions had to be different. If you do not know the initial conditions of a time process like this, then the time you get from measuring it is not an absolute. You can't say for sure, well, the time is such and such. All you can say is the time is up to that number. It's been a maximum of that amount, but not a minimum, and not an absolute. Here's a different explanation of that. If you measured the rates of these two hourglasses, this one says it's been 5 minutes and this one says it's been an hour, and you're told that they both started at the same time, then what's the correct answer? Is it 5 minutes, the one on the left, or 1 hour, the one on the right? It's got to be 5 minutes, because what happened was there was sand in this bulb when it was turned over. That's why this one has a lot of sand in the bottom, because there used to be sand in the top when it was flipped over. It wasn't set at 0 at the time. So when you have multiple hourglasses that you know started at the same time, and assuming the rates have been constant, then the shortest one is correct. Does that make sense to everybody? Because you don't know the initial conditions, and the initial conditions are determining ultimately what it looks like. So if you can get a range of answers, again, assuming constant rates and so on, then you can figure that the shortest one is going to be the closest to being correct. Now, why did I make such a big deal about that? Because when we look at the universe and even the Earth, we have multiple hourglasses we can use. And they don't all give the same answer. But as we just saw, when you have different hourglasses, it's not telling you how long it's been for sure. It's telling you how long it's been up to that amount. So you're looking for the shortest one to give you the closest answer to what actually happened. In the rest of our time here this evening, we'll be going through 20-some-odd clocks here. Some of them are giving answers, or give us answers, that are old. We'll look at clocks that say the universe is old, that say the solar system is old, and that say that the Earth is old. Then we'll go a little further and say, look at some more clocks that say these things are young. Again, universe, solar system, and Earth. What we're going to see is the ones that give us old answers for universe, solar system, and Earth are not, again, absolutes. They're saying it can be up to billions of years old, but not necessarily billions of years old. Add to that the ones that say it is much younger than that, and then we can get a more comprehensive picture. So let's start with the universe. What we're told is a really good clock to use here is distant starlight. We see stars that are a very long ways away from us. Now, the ones I'm showing you here are in our Milky Way galaxy, so these are just thousands of light years away. And a light year is the distance that light will travel in 1 year. So presumably the light came here from there over a period of thousands of years, depending on how far away they are. But we also see objects that are millions or even billions of light years away. Distant galaxies. A galaxy is a collection of, on average, 100 billion stars or so. So you see here, there's a beautiful spiral galaxy, so-called because of the spiral arms. Here's a giant elliptical galaxy, so-called because of its name. And if you can really squint your eyes, you'll see that even these little tiny dots here are also faraway galaxies. These points that you see with the lines coming off, these are stars. So there's a few stars here, here, and here. Every other little dot you see, though, is a faraway galaxy. On average, there's 100 or so billion galaxies in the universe. each of which contains about 100 billion stars on average. That works out to about 10 to the 22 stars. So write a 1 with 22 zeros after it, that's how many stars there are. That's a lot of stars. And most of them are a very long ways away from us. Now, if it would take millions or even billions of years for the light to get here, and the light is already here because we see these objects, then that would seem to indicate that these objects must actually be millions or billions, that it actually took that amount of time to get here. And that's indeed what we're told in science media and science education and so on. But again, let's look at the assumptions that have to be made. You have to assume that there's a constant rate of the process. In this case, the process is light arriving here from there. And you also have to assume you know the initial conditions. And it turns out that both of those are in question in this particular example. Constant rate. Has the speed of light always been constant through time? Personally, I don't see good evidence that it has not been, but at the same time, we haven't been here for billions of years. There are those challenging that. I think a better case can be made that the speed of light may not be constant through space. We have only ever measured the speed of light within our local neighborhood in the universe. It's possible that it travels more quickly through space where it's not being affected by gravitational fields. There are even some secular astronomers who are investigating this idea. It's not only creationists. Now, I have this in yellow just as indicate kind of a warning. That's a possibility that needs to be investigated further before we can say for sure that the rate has been constant, both through space and time. However, initial conditions is in red because that's a much bigger issue here. To say that it would take billions of years for light to travel from these faraway objects to us assumes certain things about the configuration of the universe that aren't necessarily true. And tomorrow morning I'll be getting more into this area of discussion in my Big Bang talk, so I won't spend time on it now. For now, I'll just point out that the way you model the early universe and how mass was distributed within it greatly affects how long it could have taken, or how long is required, rather, for light to get from there to here. So when you're told that it requires billions of years, that's based on certain assumptions about initial conditions, and they are only assumptions. Again, we'll talk more about that tomorrow. Another possible clock is stellar evolution. We look at the sky and we see a bewildering variety of stars. Now, you go out there with only your eye, without any equipment, and stars don't look all that different from each other. I mean, some are brighter, some are dimmer. A couple have a little bit difference in color. But when we take photographs and use other equipment, we can see that actually there's a lot of variety within them. Stars come in a variety of sizes. They come in a variety of colors. They vary in mass, composition, temperature, spin rates, and a lot of other characteristics. Now, secular astronomers have really dug into this and arranged a sequence of star evolution, by which stars move along what's called the main sequence here, and as they age, they can proceed along one path or another and wind up in various different places. And we are told that by looking at stars in this light, we can see how various stars change from one kind to another. And thus, for example, if you see our sun, you could know that it's several billion years old. I'll talk more about the sun here shortly. However, again, we're not dealing with absolutes here. We're dealing with hourglasses, which require assumptions. Here, the constant rate is not really in question because these types of sequences are based on some pretty well understood physics, or at least we think we understand it. So it's not all that questionable that it would take a long time for certain stars to change into certain other stars. What we don't know, though, is the initial conditions. How do these things form? Where do they come from? The whole stellar evolution story assumes that the stars form from clouds of gas early in the quote-unquote Big Bang universe. Well, the Bible tells us something different. The Bible tells us that God created the stars for his own glory, and indeed, star differs from star in glory. God created different kinds of stars. So the fact that there's a variety of them is just as consistent with the Bible as it is with the fact that one could have evolved from another. So my point here is hourglasses like this are really ambiguous. Depending on the initial assumptions you make, you can use them to support the Bible, or you can use them to support the evolutionary billions of years story. Now, of course, in our society, we're only told the one. But keep in mind, again, the initial assumptions you make coming into this affects the answer you get. So we see clocks that are supposed to demand an old universe don't necessarily do that. It depends on the assumptions that are made going into it. Moving a little closer to home, let's look at our solar system. Now, our solar system, of course, is made up of the sun and 8 planets. My apologies to those who are still rooting for Pluto, but Pluto lost. This diagram, of course, is not to scale. In real life, the planets are much further away from each other and the sun than this. Now, the predominant object here, at least in terms of mass, is the sun. So that's a good place to start. We are told that the sun is old. In fact, we're told that it's roughly 4.5 billion years old. And again, they will tell you all the physics that they used to get that result, but they won't tell you the assumptions that were made. The assumption here is that the star formed from a disk of gas, I should say cloud of gas, that then collapsed into a disk shape roughly 4.5 billion years ago. Now, if that assumption were true, then it's reasonable to say that it would have taken several billion years to get the sun that we see today. But again, it's only an assumption, and we need to keep that in mind. There is a secular astronomer named John Eddy who got himself in trouble with his colleagues a number of years ago when he admitted that he suspected the sun was 4.5 billion years old. However, if he was given some new and unexpected results to the contrary, and some time for some frantic recalculation and theoretical readjustment, he suspected that we could live with Bishop Ussher's age for the value for the age of the Earth and Sun, which is, of course, about 6,000 years. I don't think we have much in the way of observational evidence in astronomy to conflict with that. So that's the point I'm making. By looking at the sun, you can't tell how old it is. You have to make assumptions first. So if the biblical account is true, God created the sun to support life on Earth and for his own glory and for some other reasons. So the sun we have fits those requirements very well. It shouldn't surprise us that it is the way it is. In fact, you can actually build a lot of good design arguments from the sun, which we don't have time to do this evening, unfortunately. For now, just keep in mind, when you're told it's billions of years old, it depends on the assumptions that are made. Crater counting is another clock that's used within the solar system. We are told that by looking at craters on various objects, this is the Eratosthenes crater on the moon, that we can calculate how old these objects are because it would take a certain amount of time to accumulate all those craters. What assumptions are being made? Well, the initial conditions are an assumption that there was no craters to begin with. That's reasonable. As one creationist astronomer friend of mine has pointed out, the Bible doesn't say God did not create anything with craters. That's true. But let's give them that for now and assume that they did not have any. To use craters as a clock, you have to assume a constant rate. Is that a reasonable assumption? Well, let's see the fruit of that assumption and see if we can figure that out. When we look at the moon, we notice that it's dominated, at least the near side is, by these large dark areas. The dark areas are called maria. The maria are volcanic flows, hardened lava basically, that filled in these large basins that were believed to have been hit, or rather, what's what I'm looking for? Impacted out by objects early in the moon's history. The secular story goes like this, that the moon formed 4.5 billion years ago, and there's big problems with that story, by the way. Recent discoveries have totally discredited the giant impact theory for the moon, so secular astronomers currently have no explanation for how the moon can be there, but we'll set that aside for now. Roughly 4.3 billion years ago, the south pole of the moon got a big impact. It's actually the largest crater on the moon. After that are the impacts that we're interested in right now, in a period called the heavy bombardment, when for one reason or another, a lot of objects hit the moon, blasted out these huge impact basins, hard enough, by the way, hit the moon hard enough to actually crack the crust in places. So you see these large basins forming as a result of these impacts. Then lava starts oozing out of the cracks to fill in the basins. This is called the period of Mare volcanism. So then over time, the lava oozes out, fills in all the basins, and as that lava hardens and cools, it forms the moon that we see today. Question though, how long would it take between the impact cracking the moon's crust and the lava coming out? Short time or long time? Short time. If you were paying attention to the dates that were displayed in this little video here, evolutionists believe it took hundreds of millions of years. That the impacts happened, then the moon kind of sat around and waited for a while, thought about it. Okay, maybe I'll start oozing out some lava now, and then it came out. Why do they believe that? Because of something called ghost craters. Actually, because of two reasons. Radiometric dating is number one, which we'll talk about here shortly, and ghost craters. Ghost craters are these little craters that you see peeking up, or peeking out, of the mare areas. This is part of the highlands here. You see how this is more rugged terrain. And this is part of a mare. You see how this is a lot smoother because this is where lava flowed out and then filled in the basin. However, there's these craters peeking up out of that hardened lava. And there's a lot of these. So where do these things come from? Like you see this one here, this one's partially flooded as well. And there's traces of smaller ones here. I don't know how well you can see here. And then other things also peeking up. Well, the idea is this, that first these large impacts hit the moon, blasted out these large basins. Now, of course, the floor of the basin would be fairly smooth at that point. Then, whatever caused these craters hit inside the basins, blasted out the craters, and then after that, the lava flowed out and filled everything in. Now, there's enough craters here that at the desired secular cratering rate, it would take hundreds of millions of years to accumulate them. Therefore, that's why the evolutionists believe, I should say, secular astronomers believe that there was hundreds of millions of years of time passed in between the impacts and the lava filling it all in. That, in turn, is based on the assumption of crater rates that I mentioned earlier. So if you accept the commonly accepted rate of cratering after the bombardment periods were finished, you wind up having to accept that the moon waited several hundred million years after the impacts for lava to come out. What's the alternative? The alternative is that you don't accept that rate. The alternative is that you say, okay, well, these craters are here. Apparently, the cratering rate was higher in the past. But as soon as you say that, now you're collapsing geological time for a lot of the objects we see in the solar system, because it was supposed to take millions or billions of years to get that many craters. Ghost craters tell us that the cratering rate was actually higher in the past. That then, in turn, discredits using this as a clock to prove old objects in the solar system. So we see that within the solar system, the old clocks don't necessarily mandate old ages either. What about the Earth? Well, there's several things we can look at the Earth. And there's a bunch of these, of course. We live here, so it's easier to measure various things. Jonathan talked about some of this earlier, so I won't spend too much time. One of the primary clocks that are presented is that there's strata, meaning layers, in the geological record. And that since there's millions of layers, that must represent millions of years. Well, what assumptions are being made here? Initial conditions, well, we both agree on that. Both sides of the debate is that at one point there were no layers, and then afterward there were. The question is, how quickly were those layers laid down? If you study geology, one of the first things you'll be taught is what's called the law of superposition. That a layer on the bottom is older than a layer on top of it, unless you can show that there was some kind of geological activity that turned things over subsequently. But in general, as these things are being laid down, you have to lay down the bottom one before you can lay down one of the top ones. Now that seems to make sense, doesn't it? Turns out, though, it's not correct. As has been shown in the laboratory, as Jonathan mentioned, you can show that superposition is not true. Depending on how much sediment's in the water, how fast the water is moving, and various other things, you can actually form a bunch of layers all at the same time. So instead of one layer being laid down and then another one on top of it, another one on top of it, you actually lay a bunch of them as the water flows sideways. This is my wonderful visual effects here. But if you can imagine the layers represented by my fingers growing sideways, you can grow, quote unquote, a bunch of layers all at the same time. Is there any evidence that this has actually happened? Well, yes, there is. For one thing, we see a lot of fossils that indicate they were rapidly buried, as Jonathan mentioned earlier. This is a fish that was swallowed on the act of eating his lunch. These slides here will look familiar from the previous talk as well. This represents 3 depositional events. You see there's a line here and a line here. This, and this, they were each laid down in a matter of hours, not millions of years. And indeed, the layering even within these are very fine, as you can see. So even lots of layers being laid down quickly can indicate short times rather than long. Jonathan also mentioned polystrate fossils, fossils that cut across multiple layers. Again, now we're collapsing the amount of time that those layers represent. The layers themselves are sometimes folded. Now, has anybody ever tried to fold a rock? Doesn't work very well, right? Yet in various places we see that rocks are very sharply folded. Now it turns out that you can actually fold rock if you keep it under enough heat and pressure, but that actually does certain things to the rock. It metamorphosizes it. But in various places we see some very sharp folding with no evidence of that occurring. For scale here, here's two people, by the way. The only way this could have happened is if all those layers were still unconsolidated. They weren't rock yet. They were still at least partially wet sediment. Well, that tells you then in turn that it didn't take millions of years, or however many layers that is, to lay all that down. It had to all have been soft at once, therefore it was all laid down at once. Now we're talking about a massive flood rather than millions of years. You see, even within the layers, there are things we would expect to see if it represented a long time. But we don't see these things. An example is bioturbation. The disturbing of this material by biological activity. For example, here in the Sound we have gooey ducks. Am I pronouncing that correctly? The fact that anybody would eat those things astounds me. But anyway, what do they do? I mean, they burrow into the bottom of the Sound, right? When you have a layer that's exposed to an oceanic or a water environment, you have plants growing, you have clams and everything else digging and burrowing. There's evidence that this occurred later. Well, we don't often see bioturbation in the record. That would indicate that those layers were not actually exposed to water very long. Jonathan mentioned footprints, ripple marks, and other things that we would not expect to see if those layers had been exposed for long periods of time before being covered up by something else. We also have things like this. Hard to see from the back, I apologize, but this is actually a unique kind of fossil. It's a dinosaur fossil, but it's not a bone. It's called a coprolite. And I get a few knowing grins here from people in the audience. When I give school talks, I like to pass this around to the kids and ask them to figure out what it is. And I ask them if it has a smell or like this, try to figure it out. This is fossilized dinosaur dung. And it's fun seeing their expressions when I reveal that fact to them after they've been handling it. Now, if the neighbor's dog leaves one of these deposits in your yard, does it sit there for years and years until gradual layers of sediment cover it up and it becomes a fossil? Or does insect, wind, rain, and other activity dissipate it fairly quickly? Well, you would think that if it took long periods of time to lay down these layers, you wouldn't see this kind of stuff, but we do find a lot of it. There are paleontologists who specialize in this. Yeah. I saw one had a whole table full of the stuff. Now, this one is kind of squished. Maybe the dinosaur had diarrhea or something. But these particular specimens, I mean, it looked like what it was. So, and they're sawing it open and trying to figure out, what it contained, and yeah. Strange way to make a living. My point is, as I hope is obvious, is this stuff would indicate that it was all buried fairly quickly. So millions of layers does not indicate millions of years. Do the canyons that we see exposed here require millions of years to form? Jonathan talked about this as well, so I won't spend too much time on it. Flowing water has tremendous destructive force. There's various mechanisms for erosion, and the more water and the faster it's moving, the worse it gets. Glen Canyon Dam. This is a spillway tunnel that was opened basically beyond its design capacity because the reservoir behind it was building up to dangerous levels. In a period of a couple days, catastrophic cavitation started occurring here, and several feet of steel rebar reinforced concrete was eaten through by erosion and then down into the rock. Mount St. Helens, I believe Jonathan had this slide as well. These canyons formed very quickly. Burlingame Canyon. This canyon system formed in 6 days. Canyon Lake Gorge formed in 3 days. There's lots of examples of catastrophic erosion causing canyons to form in a fairly short period of time. So no, a canyon does not require millions of years or long periods of time. In fact, as Jonathan also mentioned, which came first, the canyon or the river? Well, the canyon came first, and then this little river is here now because water flows downhill, of course. So if you had this big gash in the ground, that's where the water flows into. Moving onwards, we have radiometric dating. Now, this is a big one, of course, and this is the one that the evolutionists think they got it all locked in. This proves without a doubt that everything is old. How does this work? Well, as an example, we'll take uranium, symbol U, to lead, Pb. That system has a half-life of about 4.5 billion years, give or take. What does that mean? That means if you started out with a brick of uranium and you waited 4.5 billion years, that half of it would turn into lead. Now, in real life, it wouldn't be half on the bottom, half on top. They'd be scattered throughout, but I'm doing this for illustration purposes. So after one half-life, half of what you started with is gone and turned into the daughter product. After another half-life, half of what you had is gone as well. And so it goes. So the idea is that by measuring the ratio of parent to daughter, we can figure out how long it's been since the system started at 0. But again, we're not dealing with clocks or watches here. We're dealing with hourglasses. You have to make assumptions. In this case, both assumptions can be challenged. You have to assume that the rate of decay of transforming one element to another has been constant, and you have to assume that you know the initial conditions. More specifically, in this case, the assumptions that have to be made is that there's no change in the rate, as I mentioned a moment ago. You have to assume that no daughter element was present in the beginning for some of these methods. You also have to assume that no parent or daughter element was added to or subtracted from the system. More explicitly here, if you had a change in the decay rate, then you can't say how long it was to produce the system that you see here, can you? It would depend on what the rate was in the past. Also, too, if you assume here that there's no daughter initially, if there was a daughter, it makes the sample look old, doesn't it? Because you say, well, in this contrived example, you say this is half and half, so it must be 4.5 billion years old. Well, actually, no, it could be very young. Maybe it had lead to begin with. Since you weren't there when it was formed, you don't know whether or not that's true or not. In similar form, if you add daughter or subtract daughter from the system, or change the amount of parent in the system, again, you get something that's not reflective of its true age. Now, there are some technical details here, and there are some methods that try to avoid making some of these assumptions. To do that, however, they need to make additional assumptions, and I don't want to bore anybody. So let's just ask a more obvious question. Does it work? If you take a rock and you date it multiple ways, do you get consistent answers? Well, here's a cutaway view of the Grand Canyon. Now, creationists and evolutionists argue about how long it's been since the system was formed, but both agree on the relative order that things happened. These layers down here were laid down first. Then there was some kind of an erosional event that cut across this way. Then further layers were laid down. Then there was a massive erosion here that caused the Grand Canyon itself. And last of all, volcanic activity up here had this formation that trickles down into the canyon. Now, people have taken samples from various places and submitted them for dating. And it's interesting when you realize that this basaltic rock here, produced by the volcanoes on the top, which everybody agrees is the youngest of the whole system, when you date it different ways, you get a wide range of ages, going from 10,000 years all the way up to 2.6 billion years for the same rock. Take a sample from down here, submit that, you get a range of 791 to 1.07 billion. Notice that the oldest age up here is actually older than the oldest age for the one down below. And there's a lot of examples of this in creationist material, as I'm sure some of you have seen. Steve Austin took a sample from the Mount St. Helens lava dome. Now, we know when this thing formed. He submitted it for potassium to argon dating, which is specifically designed to tell you how long it's been since lava hardened into rock. The age he got back for the lava dome was 340,000 to 2.8 million years, when in reality it was 6 years old at the time he sent it in. Now, I saw an atheist blowing steam on this on the internet saying, well, he's being deceptive about the whole thing because everybody knows that potassium argon can't work unless the sample is X amount old. And that since he knew it was very young, he should have known it would have produced these erroneously old ages. I said, well, no, that's the whole point. The whole point is that the age, this method always gives you old ages, even when it is young. So when you test a method using young rocks and it tells you old ages, why should you believe the old ages for a rock that you don't already know the age of? Right? Other examples of this. There's a crater in Arizona, formed in 1065. Potassium argon says it's 210,000 years old. Sample from there. Lava flows in New Zealand. Various methods here. The sample is only about 50 years old at the time. You can see the wide range of ages that it got. Notice for you geology geeks here, some of these are isochron ages, which are supposed to eliminate some of the assumptions I mentioned earlier. Yet they still produce ages that are millions of years too high. In this case, 3.9 billion years for a sample that was about 50 years old. Basalt in Hawaii, similar thing. Only a couple hundred years old, but we got ages of up to 22 million. Now, some people say, okay, so some of these methods may have some problems. Nevertheless, though, they still consistently produce ages up in the millions of years. So doesn't that still show that things are young? Not necessarily. Again, we're making assumptions here, so let's look at that. I'm showing you here some zircon crystals. Now, those, I assume, this is a dangerous word to use in this presentation, I'm assuming that there's some copies of the rate materials out on the book tables out there, if anybody wants more details of what I'm about to talk about. But there was a long project that looked at the decay within zircon crystals of uranium. And it turns out that to go from uranium-238 to lead-206, along that decay chain, 8 helium atoms are produced. It also turns out that in the particular zircon crystals that were studied, there's a lot of excess helium. Now, this is interesting because helium, of course, is a very small molecule and very light. I mean, that's why helium balloons float, right? And helium can migrate through rock fairly easily. So if these rocks were actually old, there should not have been this much helium still within them, but there was. The scientists who studied this actually plotted out and said, well, the creation model that says these rocks are only 6,000 years old would indicate that helium diffuses out of the rock at this certain rate. And here's the graph for that. Conversely, if these rocks are billions of years old, helium would have to diffuse much more slowly than we would otherwise think would be the case, and it would indicate down here. So they actually sent off for testing to find out what the diffusion rate of helium is in this particular circumstance, and the data came back that matched up, as you can see, very consistently with the creation prediction, off by a factor of 100,000 with the deep time model. My point in all this is that there is evidence that there has been a lot of decay, radioactive decay, in the past. That's why all the helium is there. There's other evidence for this as well, fission tracks and radiohalos and some other things. But that decay apparently happened in a very short time because the helium is still there. It hasn't had time to leak out yet. Does that make sense? I'm throwing a lot at you from different topics. So for old clocks, we've been through a few that purport to require old ages for the universe, the solar system, and the Earth. And we find that although these methods do produce old ages, they're not absolute ages. They're up to that age, depending on what assumptions are being made. On the other hand, there are many clocks we can use to show that things are actually young. So let's take the same order. We'll go the universe first, then the solar system, and then down to Earth. Out in the universe, there's something called the missing intracluster medium. What is that? Well, this is a globular cluster. Globular clusters are large collections of stars that, as you can probably guess by the name, are spherically shaped. And galaxies typically have a lot of these things orbiting them. This is a galaxy. There's a lot of dwarf galaxies and globular clusters that are typically found in the halo. Let there be light. The Milky Way has over 100 of these things. Other larger galaxies we've seen have hundreds of globular clusters. Now this is interesting because it can take up to 1 billion years for a globular cluster to make an orbit around one of these galaxies. And it also turns out that within these clusters, of course these are thousands or hundreds of thousands of stars in these things. As stars produce stellar wind, they're blowing material out into the space in between them. It turns out that that material remains in the clusters until they pass through the plane of the galaxy they're orbiting. So as they're out here, they're accumulating dust and grains and other things. When they come through here, they're cleansed of that, and then they build up more and more and more and more until they're cleansed, and so on. The interesting thing is, like I said, it takes up to 1 billion years for these things to orbit the galaxy. There should be a lot of material built up in the intracluster spaces here that we do not find. They've gone looking for dust and other materials in between the stars here, and a lot of these things is missing. Depending on which numbers you use, there's anywhere from just 10% of what should be there down to just 1% of what should be there. So that cuts your billion-year age down to 100 million to maybe just 1 million. So we see a clock that its maximum now is much shorter than what would otherwise be expected by the secular timescales. The solar system provides us a lot of these, and I only have time to do a few tonight. One of them is short-period comets. What is a short-period comet? Well, a comet is basically a big dirty snowball in space. Here's an actual photograph of the Wild 2 comet. It's about 3 miles across, so that gives you an idea how big it is. Now, you generally can't see the nucleus because it's obscured by everything else that's going on. For most of its orbit around the sun, a comet is not necessarily all that exciting to look at. In fact, we usually can't see them because they're small and dark and far away. However, as they approach the sun heats them up, and the ices within the comet start to sublimate into gas. The gas comes out in jets, and then that in turn forms the beautiful tail that we see from Earth. Now think about that. That means that the comet is actually burning up material each time it approaches the sun. And indeed, comets do lose material. And in fact, comets, each one of them that you see, is doomed because a comet can only survive so many trips around the sun before it's all burned away. What I'm showing you here is fragments of a comet. We've actually seen several dozen comets break up like this. Some comets do manage to avoid being burned up by the sun, but only because they crash into a planet like Jupiter or interact gravitationally with something and get flung out of the solar system completely, never to return. So whichever one of those three fates it suffers, every comet you see may be beautiful, but it's also temporary and doomed. Now you can calculate how long of a lifespan, if I can apply that word to a snowball, these comets have as they orbit the sun. And the answer turns out to be about 10,000 years. Now the secular model says comets could only have formed in the very beginning of the solar system's formation, which was supposed to be 4.5 billion years ago. Their model can't make them after that time. Therefore, if the solar system was older than 10,000 years, we shouldn't see these comets anymore. But we do. That would seem to indicate that the solar system is less than 10,000 years old. Do evolutionists and secular astronomers have an answer for this? Well, yes, they do. Or they think they do. They will tell you that there's two vast reservoirs of cometary nuclei out there in space that occasionally come in and become new comets to keep resupplying the comets that we see. There's one called the Kuiper belt, which is a narrow belt of nuclei, supposedly, that orbits roughly outside of Pluto's orbit. And then there's the Oort cloud, this vast spherical shape cloud of nuclei that's believed to be out there in space. Now, they need both of these reservoirs for different reasons. It turns out both of them have serious problems. They've gone looking for Kuiper belt comets and only found a tiny, tiny fraction of the number they need in order to keep producing comets for billions of years. The Oort cloud also is running into problems. They figured out that they need about 400 billion comets out there in the Oort cloud to keep supplying them for all this time it's been since the beginning of the solar system. The problem is more involved calculations and examinations of the model says the secular model can only make 6 billion comets out there. So obviously those two numbers don't match. You need 400 billion to keep having comets today after billions of years, but the secular model at its best can make only 6 billion. What's the solution for this? Well, the solution is that the sun stole its comets from other stars. I'm not making this up. There are planetary scientists who are seriously proposing this as a solution, and here's how it works. Basically, they say that the sun was born in a large cluster with hundreds of other stars, all born in the same gas cloud. In that birth cluster, the stars were close enough together to pull comets away from each other via gravity. And Hal Levison, this astronomer being quoted here, said it's hard to imagine it not happening. I mean, of course it would happen. Well, let's think about this for a minute. So the reason they're resorting to this in the first place is that a gas cloud around a star can't make the comets they need. So if our sun couldn't have made them, why can other stars make them instead, if it's the same type of process? That's problem number one. Problem number two is this requires the sun to have a lot of companions that it formed with. Well, our sun is a single star. There are no companions today. They say, well, they went elsewhere. They're gone now. Well, now you're making up stories instead of looking at data, aren't you? Third problem. As they say here, the stars are close enough to pull comets away from each other via gravity. Why didn't any of the other stars pull comets from our sun instead of the other way around? I mean, is there like a one-way comet valve in space that allowed our sun to take them but not give any up? And I like the conclusion. It's hard to imagine it not happening. See, this is the problem with us creationists. We don't have enough imaginations. See, if we had better imaginations, then we could see the evidence for evolution. Anyway, I'm including this here just to show that the various things I'm talking about, there are proposed solutions from the secular camp, but most of them are about as good as this one. Saturn's rings. Lord willing, we're going to try to look at Saturn tonight. And of course, Saturn's famous for its beautiful rings, but do the rings tell us anything about the age of this system? Well, even though they're called rings, they're not actually rings. They're more like belts of particles. The rings are actually very thin compared to Saturn's bulk. And they're composed basically of a lot of particles, rocks, maybe boulder-sized objects, all orbiting Saturn together, and they happen to be organized in certain patterns that make these beautiful rings. The fact that we can see the rings, though, is a problem for the secular model. As Saturn moves through space, it's collecting dirt, for lack of a better word, interplanetary material that over time gets absorbed into the rings and darkens them. It turns out it should take only a couple 100 million years for Saturn's rings to be darkened. But they're not darkened, they're very bright, as we can see in the photograph here. Now, here I'm showing you a clock that has a maximum age of a couple 100 million years versus the 4.5 billion years it's supposed to be. Now, that may sound like a long time, and it is, but keep two things in mind. Number one, that's a maximum age, not an absolute age. And number two, a couple 100 million years, if you say that's how old these things are, you've still eliminated 95% of the 4.5 billion year age that is supposed to be the answer here. Moving on, we have a couple of moons of Saturn that are interesting. One is called Enceladus. And Enceladus is a bright little moon that does something very interesting. There's a photograph of Enceladus actually below Saturn's rings. And maybe you can see, if the light's good enough in here, there's a little smudge beneath that moon. We took close-ups and investigated this further. We found out Enceladus has water geysers coming out of its south pole. Now, the problem here is Enceladus is a tiny little moon. If it formed billions of years ago from this gas cloud that we're told about, it should have cooled off from that formation long ago. It receives a little bit of energy from tidal effects with Saturn, but not enough to be powering any geological activity today. Enceladus, according to the secular model, is too old to be geologically active, but it is geologically active. This is a false color picture. You can see the extent of this material coming out into space. This moon does not look billions of years old. Neither does its neighbor, Titan. Titan, as you can probably guess by the name, is a very large moon. And as you can see by looking at it, it's fuzzy. It's not a bad picture. That's how the thing actually looks. Titan actually has an atmosphere. Now, this gets interesting because we can't see through the atmosphere from telescopes on Earth, but what we can do is analyze sunlight bouncing off of it and figure out what is in the atmosphere. It turns out that Titan has a lot of methane. Now, that's interesting because methane gets broken down by sunlight, fairly rapidly, in fact. In fact, they've calculated that it would take only 10 million years to break down all the methane in Titan's atmosphere and turn it into ethane and other chemicals. But it's supposed to be 4.5 billion years old. So how do you solve this one? Well, they said, okay, well, that means apparently there's some reservoir of methane on Titan that keeps resupplying its atmosphere over these billions of years. At the same time, there must also be a vast growing reservoir of ethane on Titan from all the methane that's been broken down for 4.5 billion years. So before we got to Titan, secular astronomers were confidently predicting that there was this deep global ocean of methane and ethane on Titan. And I say ocean because Titan's very cold. Those things would be liquid. So it was a real surprise then when we actually sent a lander down through the clouds and found out that Titan's surface is dry. Again, only 10 million years worth of methane in the atmosphere. After 10 million years, it should all be gone, but it's still there. Moving in a little closer to the solar system, we have the planet Jupiter, which has a moon called Io, which also can provide an interesting clock for us. Io is sometimes called the pizza moon, because that's kind of what it looks like. Io is also famous because it's the most volcanically active place in the solar system. It has enormous volcanoes on it, as you can see, and that's just one here from the arrow. At any given time, there seems to be multiple volcanoes going off, blasting material up more than 100 miles into space in some cases. We have seen some volcanic eruptions on Io produce 100 cubic meters of lava per second. Some of these flows are as big as southwestern states like Nevada, Arizona. Enormous amounts of material are coming out of this little moon. Now, the same kind of reasoning applies to Io as it did to Enceladus. Io is not very big. Should have cooled off after its formation a long time ago. Shouldn't have geological activity still going on. Now, Io is orbiting Jupiter, and it is caught in a gravitational tug-of-war between Jupiter and some of its other moons. So Io is being flexed and squeezed, and the secular astronomers claim that this is where all the energy is coming from to keep doing this. There are problems, though. There's a recent discovery that the expected pattern of heat dissipation on Io is different than what it would be if Jupiter and tidal effects were actually powering all of this. But more to the point, the amount of material coming out of Io is just staggering when you can think of how big the moon actually is. I don't know if you can read this, but it says, we conservatively estimate that Io should have produced 10 to the 12 cubic kilometers of magma. However, the total volume is only 2.5 times 10 to the 10. In other words, if Io is over 4 billion years old, it's recycled itself through its own volcanoes over 40 times. Now it gets more interesting. Io should have undergone, on average, well over 100 episodes of partial melting. This surely has resulted in extensive differentiation. Now, when an astronomer talks about differentiation, he's talking about different weights of materials, or I should say different densities of materials, sorting themselves out. And so like on the Earth, you have core, mantle, crust. Io should have undergone this as well, especially because there's enough heat, as it says, to have partially melted the moon over 100 times. What do you have when there's different materials, different liquids especially, all mixed together? Well, the lighter ones float and the heavier ones sink, right? That's why like the Galilean thermometer is based on this principle. This is a fun homeschool project, by the way. Build one of these. Turns out, Io should have differentiated itself. The heavier magma should have sank, and the lighter should have floated above it. And there should be a light density crust on Io by now, but that's not the case. By looking at some of the lavas that are coming out of Io, they're very dense. They're ultramafic. Those should not be coming out of the volcanoes anymore. All the heavier stuff should have sank down inside the moon. The fact that it hasn't sank down yet means there hasn't been enough time to do so, unless you want to start questioning whether or not light things float and heavy things sink. Moving on, time is really getting away from me here. The planet Mercury. Interesting little planet, smaller than some of the moons elsewhere in the solar system. Secular astronomers were quite surprised in the mid-70s when we first flew a spacecraft by this thing and found out it has a magnetic field. Mercury is small enough that it should have cooled off from its formation long ago, according to the secular model. And one of the implications of that is that Mercury shouldn't have a magnetic field anymore. It turns out it does. That would seem to indicate that the secular model has some real problems to explain. It was then a further unpleasant surprise here a couple years ago when the Messenger spacecraft revisited Mercury and found out that this magnetic field, which evolutionists can't explain, is also decaying fairly rapidly. It's gone down 7.8% since its first measurement in the mid-70s. Work that out, it's a half-life of just 320 years. Now, as I already said, Mercury shouldn't have a magnetic field in the first place, but if it does have one, then it's obviously been stable for 4.5 billion years if the secular model is true. That being the case, we would expect it to be stable today, but it's not. It's decaying very rapidly. It looks like a field that was recently created, and this concords very well with some creationist predictions that were made. I don't have time to go into this, but there have been actually some predictions by creationists as to what we would find when we visited some of these planets before we had actually done so. The measurements matched the creationist predictions, did not match the secular predictions. Lunar recession, another clock we can use. We look at the moon. Of course, we know it orbits the Earth. What we don't realize, though, is that the moon is actually moving away from the Earth slightly every year. Why is it doing that? Well, the moon's gravity raises tidal bulges on the Earth. What's not shown on the diagram here is that the Earth is actually spinning more rapidly than the moon is orbiting. Now, that's how we experience tides. I mean, we look and we see the ocean rising and falling, or we think that's what we see. What's actually happening is, as we stand in one place on the Earth, we rotate into a tidal bulge and then back out of it. So the moon is receding because there's a slight amount of friction between the Earth and that ocean bulge. As the Earth rotates, it pulls that bulge slightly forward. Now, this is a big mass of ocean water. It exerts a separate gravitational pull on the moon than the Earth does, and as you can see, it's somewhat offset. That produces a slight sideways pull on the moon and accelerates it in its orbit. And the way orbits work is when you accelerate it, it moves further away. So this was all understood and anticipated before we actually arrived on the moon. But we were able to measure more accurately as a result of the Apollo program. One of the experiments that the astronauts brought up, if you can see this device back here, here's a close-up look of it, a little pixelated maybe. It's basically a very sophisticated mirror. Not actually a mirror, but it serves the same purpose. It's a reflector. And there have been several of these left behind on the moon. Apollo 11, 14, and 15 each left behind one of these devices on the moon. And using these, we were able to bounce laser beams from Earth off the reflector and measure how long it takes for the beam to come back to us. Now, as you can guess, that's not easy to do. I mean, you're firing at that small of a target on the moon. But they are able to do this. And as we measure year by year, we are indeed observing that the moon is moving further away from us. Now, it's not much. It's only 1.5 inches or so per year. But the way this works is because it's a gravitational tidal effect, it would have been stronger in the past. And do the math on this, the moon would have been touching the Earth only about 1.5 billion years ago. But this system is supposed to be 4 billion years old. So we've just chopped 2.5 billion years off of the system. Now again, I'm not saying it is 1.5 billion years old. That's a maximum age. The system is up to that age, but not up to 4 billion. Now the secular crowd has tried to come up with explanations for this, and basically they say if you rearrange the Earth's continents and do some other things early in Earth's history, then that makes the recession rate less, and so this effect wouldn't have happened, blah, blah, blah. There's problems with their explanations. I don't have time to get into it tonight. If anybody's curious, you can come talk to me. Among other things, they're ignoring some new oceanography work that was done that shows friction occurs even in deep ocean basins, not just the shallow seas. For now, though, I will just point out that there are actually clocks that do not agree in the solar system with 4.5 billion years. What about the Earth itself? Are there young clocks here? Well, yes, there are. One thing is salt in the oceans. Anybody ever wonder why the ocean's salty? Well, it's because rainwater comes down on the continents and washes material into the oceans. And it turns out there's actually an increasing amount of salt going into the ocean every year. The ocean gets saltier all the time. There's about 450 million tons of the stuff going into the ocean each year. Now, there's some that comes out through various means, but that's only about 27% of the input, which is why, as I said, it's building up. Now work it backwards. How long would it have taken at current rates to build up all the salt in the oceans that we see? And the answer is about 62 million. Again, that's a maximum, not an absolute. But the oceans are supposed to be billions of years old. Ocean sediment, same kind of argument. We measure how much mud and sediment is on the ocean floor. Each year there's a net inflow of the stuff. Maximum age here is now down to 15 million years. Continental erosion. We can measure how much material gets eroded off the continents, wind, rain, and so on. Turns out that all the continents would be eroded down to sea level in just 14 million years. Now, the secular answer here is that, well, over time, tectonic activity is pushing up new mountains and so on. Well, yeah, but that means that there should be no mountain older than 14 million years, right? But there are some claim to be much older than that. Earth's magnetism. Now, unless you use a compass, you probably don't pay much attention to our magnetic field, but it's actually vital to you sitting in this room because, among other things, the magnetic field protects us from harmful radiation from the sun. It also turns out that the field is decaying. Since 1829, which is when we started taking good measurements, the total energy in the field has fallen by about 14%. Now, that doesn't sound like much, but when you work this out, it loses about half of its energy every 1,400 years or so. So in 600 AD, the field was twice as strong as it is today. In 800 BC, it was 4 times as strong. In 2200 BC, it was 8 times as strong, and so on. So you see how it builds up very quickly as you go back. Now, I'm not talking about polarity reversals here. You may have heard that the northern and southern magnetic poles have swapped in the past. That's not what we're talking about. We're talking about the energy in the field. Why is this important? Because the strength of the field is believed to be a reflection of the current inside the Earth's core that produces it, and that in turn is related to the heat that is produced as part of this process. Is there a maximum amount of heat that we can figure out the Earth has ever had? And the answer is yes. You can figure out how much heat would be required Da-da-da-da. You can figure out how much heat would be required in order to melt the Earth's crust. Now, there's no evidence that that's actually happened, so we can safely say that's a maximum amount of heat. Working backwards then from that maximum amount of heat, we can figure out a maximum strength for the magnetic field, and thus how old it could have been according to its decay rate, and the answer there is about 20,000 years, not billions. Moving on, carbon dating. Jonathan talked about this a little bit. You also use the specific example that even if the entire Earth were made of carbon, it would all be carbon-14, excuse me. It would all be gone in 1,000,000 years because carbon-14 decays very quickly. That being the case, if an object were actually millions of years old, we would not find radiometric carbon-14, I should say radioactive carbon-14, within it. But we do. Petrified wood, for example. Their sample is supposed to be millions of years old, but still has carbon-14 within it. Coal, up to hundreds of millions of years old, supposedly, yet still has carbon-14 in it. Oil, same thing. Diamonds, as Jonathan mentioned, supposed to be up to 3 billion years, but there's still carbon-14 within it. Again, the carbon-14 is gone after a few thousand years. It's hard to measure anyway. There's only one atom of these to 1 trillion, actually over 1 trillion, normal carbon atoms. So even after just a few thousand years of decay, it starts getting very difficult to measure. It's certainly gone after long periods of time. So carbon-14 in all these objects tells us these objects are actually thousands of years old, not millions. I'm going to skip this one because I'm running low on time. And get to the last one, dinosaurs. Now, if you're new to a creation conference or the creation movement in general, you're probably scratching your head saying, what is a creationist doing talking about dinosaurs? Aren't dinosaurs the nail in the creationist coffin? Well, no. We love dinosaurs. For example, there are places where there are unfossilized dinosaur bones to be found. The North Shore of Alaska, for example, has unfossilized lambeosaur bones sticking out of the riverbank. Locals knew about it for a while, but thought they were buffalo bones, so didn't say anything to anybody. Turns out they're dinosaur bones. Unfossilized. Within even fossilized dinosaur bones, we're finding bone proteins. These shouldn't be there if these things were millions of years old. There have been several samples of dinosaur tissue, dinosaur bones specifically, submitted for radiocarbon dating. Turns out it has measurable carbon-14 within it. Again, carbon-14 is gone after just a few thousand years. These things are supposed to be older than 65 million years, yet they still have carbon within them. This is a picture of the Hell Creek Formation in Montana, which is a fairly rich area for dinosaur fossils. A number of years ago, a paleontologist named Mary Schweitzer was excavating a tyrannosaur leg bone and had trouble getting it out as a remote location, so they reluctantly cut it in half. And when they saw the cross-section, they saw something which interested them. So they went back to the lab, did some work, dissolved away some of the outer material, and found inside of a tyrannosaur thigh bone soft, stretchy tissue. Does this look 65 million years old? She commented that it was totally shocking. She didn't believe it until they'd done it 17 times. Subsequent investigation revealed what appears to be blood vessels and blood cells. Dinosaur blood. No, this doesn't mean Jurassic Park is going to happen next year. Everybody always asks that. But should this be there after 65 million years? No. Neither should DNA. In fact, we have actual numbers on this one because people have studied how quickly DNA decomposes and breaks down. Turns out that even if you freeze a biological sample, it's estimated that after just 6.8 million years, the DNA is gone. These bones are supposed to be 65 million years old and older than that, yet they still have DNA within them. What does that tell you? Now, I've just covered a wide variety of different topics here tonight. And some of you might be wondering, well, all these different ages, which one is the correct one? Well, let's return to a point I made earlier. When there's multiple hourglasses, note to self, put some kind of gray background behind here so people can see the hourglasses. When there's multiple hourglasses, the shortest one's correct. Remember the reasoning we used with that? Here's the variety of clocks that we talked about tonight. Now, they apply to different locations, and they range from 13.7 billion all the way down to about 10,000. That being the case, since these work like hourglasses and not stopwatches, the shortest ones are the ones that are going to be correct. So if there's one takeaway from the talk tonight, it's this: up to. What do I mean by that? Well, as you're reading science magazines, seeing science programs, whatever it may be, you're going to hear over and over again about millions of years this and billions of years that. Mentally fill in the words up to. This coprolite is up to 65 million years old. But that's based on assumptions that are made. Using other clocks, we can say, no, dinosaurs were apparently just thousands of years ago, and that's actually the correct number to go with. So there's other clocks I haven't had time to discuss tonight, but they all have similar assumptions. Again, you're going to be told millions of years this and billions of years that. Remember, that clock says up to billions, but I have other clocks that say up to thousands. It's similar to playing a game. If someone asks you, I'm thinking of a number, I want you to guess what it is. You say, well, give me a clue. Okay, it's between 1 and 100. Give me another clue. Okay, it's between 1 and 50. Give me a third clue. Okay, it's between 1 and 5. How many choices do you have now? 5, right? Because those are the only numbers that match all 3 clues. So same thing here. We have a bunch of different clues. Some give ranges of up to 13.7 billion. Now, that's a pretty big range. Others say, well, no, 10,000. For both of those measurements to be accurate, you got to say, I got to limit my final answer to the smaller range. So one thing I hope people who are perhaps new to this discussion will also take away from tonight is that the creation versus evolution discussion controversy is not science versus religion. It's not that they have the science and we're just blindly trusting in our book. There's a lot of scientific reasons to think that things are actually a lot younger than what is told. Without sounding like a conspiracy theorist, I wonder, why is it that the things that are focused on in the media are the billions of years ages, and you don't hear much about the dinosaur DNA? Or short-period comets and the Oort cloud being underpopulated, or fill in the blank. As I hope I've made clear, there's a lot of clocks that give very tight age ranges for Earth, solar system, broader extension of the universe. But the ones that are always presented to us are always the ones that are 4.5 billion year Earth, 4.5 billion year solar system, 13 billion year universe. I leave it to you to decide why that is.